Hi students, all of you welcome. Welcome to Suneel Engineering Academy. I am Sunil Kumar Bandaru. Students, in this Transformers through topic wise MCQ series, we have completed 6 sessions. This is the seventh one. If you want previous, click on the playlist. You can find out the previous session. And don't forget to subscribe. Okay. So let me check up to which we have completed in the previous. And all of you try to join in the Telegram group, guys. I have given the link in the description box. Click on the link and join the Telegram group. Okay. So in last also so many questions completed na. Yes. So this one. The first question is this: eddy current loss in ferromagnetic core is proportional to dash. In the previous session, I have already given eddy current. Trick also I have given simply eddy square, d into d square. So all the terms are in square. B max square, F square, T square. Okay. So thickness of lamination T. So proportional to frequency square. Okay. So square of frequency. If you can consider hysteresis losses, zeta into B max power 1.6 F into V. Here only proportional with the frequency only. Okay. Coming to the next question. Transformer core is laminated to dash. A very easy question, very repeated question. Transformer core is laminated to reduce the eddy current losses. Okay. So why we are going with the lamination? So by using the lamination, we can reduce the area of the cross section. Whenever the area is reduces, R is equal to rho L by A. As area is less, resistance is more. Resistance is more means eddy currents are less. So whenever the eddy currents are less, then eddy current is less, then eddy current losses are also less. Okay, what are these eddy currents? So many having doubt on this. For example, if this is a magnetic core, okay, so here the currents which are circulated within the core, okay, the currents which are circulated within the core itself is nothing but eddy current loss, eddy currents. Okay, so due to that we are getting the heat, so that is in the form of losses. So we are getting eddy current losses. Whenever this area is less, then there is no chance of circulation. Okay, so the circulating current is reduced, then eddy current will be reduced. We can understand this one by using our real-time example. Whenever the road is wide, that is like 40 feet, then the vehicles can easily circulate within that road. If anyone wants to circulate within that road, they can easily circulate. So there is a chance of eddy current losses. Okay. So, but whenever the road is like just a 5 feet road, okay. If the car want to circulate within that, no. Bus want to circulate within that one, no. So that means vehicles difficult to circulate. Okay, difficult to circulate, and they can also move very slowly. So that means you can say the current is less, eddy current, that is circulating current is less. The same happen here. So that means here if you reduce the road area, that means road width, then the vehicles cannot circulate. In the same way, if you reduce the area of the core, the eddy currents cannot circulate. For that purpose, we are going to take a small cross sectional area like this, and we are bunching them together to form a single core. Okay, to form a single core. Okay, these are the nothing but lamination type of the laminated cores. Like same book, if you know, single page is very less mechanical strength. So we are bunching all them together to form a single book. Okay. In general, the transformer core laminations are insulated from each other by which? By cotton, by mica, the thin coat of varnish, none of the above. So generally we use thin coat of varnish. Okay. The thickness of laminations used in transformer. So generally the thickness of laminations are 0.4 mm to 0.5 mm. Okay. So if you want to go further, then also eddy current losses will be decreased. But what is the problem? So manufacturing cost will be increased. If you want to get very thin laminated cores, that is cost is also very high. Okay, so that is like a precision materials are required to cut that much of small thickness. Okay, coming to the next question. The single phase transformer 220 bar 440 volts 50 hertz operates at no load 220 volt 40 hertz. The frequency operation rated voltage result in which of the following? So they're asking about the losses question. I said already, whenever you are getting losses question, first of all you have to check V by F is constant, that is V max is constant or not. Okay. So 220 volt 50 hertz, here 220 volt 40 hertz. So V by F is not constant. F is not constant, but voltage is constant. By keeping voltage as constant and frequency is reduces, then what happened to the hysteresis and eddy current losses? Okay, so V by F is not constant. What about the hysteresis losses? A V power 1.6 by F power 0.6 now. If it is a constant, WH is inversely proportional to frequency. So frequency decreases means hysteresis losses will be increases. Okay, increase of hysteresis losses. And coming to the next one, eddy current losses. Eddy current losses, if the V by F is not constant, then WH is equal to BV square. It depends upon only voltage. So here frequency increases or decreases, there is no change. So no change. Here no change. So increase of hysteresis losses and no change in the eddy current losses. I have given this table. If the V by F is constant, what is the hysteresis and eddy current? V by F is not constant, what are the hysteresis and eddy current losses? Okay, in the previous session. So please try to watch that one, then you will get this one as very easily. Coming to the next one, if the frequency is increased by keeping the voltage as constant. Voltage constant, frequency increases. Okay, that means V by F is not constant. One constant, one increases means V by F is not constant. Okay, and V is constant. Then what about the hysteresis losses? Generally inversely proportional to F power 0.6 now. And eddy current loss is proportional to V square. So V is constant here. So eddy current losses will be constant. Eddy current losses will be constant. As frequency increases, hysteresis losses will be decreased. So here hysteresis loss are decreased and eddy current losses will be unchanged. So the answer is option D. Okay, constant, these are decreased. Coming to the next question. What would happen if power transformer designed for operation on 50 Hz were connected to 500 Hz of the same voltage? Whenever the frequency increases, what will happen? About the hysteresis losses, just now we have discussed now, inversely proportional to 0.6. Frequency increases means hysteresis losses will be decreases. Eddy current losses will be constant, same. Okay, for the same voltage if the frequency varies, this will be constant. So here current will be too much high. Transformer may start smoke and burn. Losses will be excessive. This is the most probable answer. So that's why I have given the answer is this. Okay. Coming to the next one. The voltage applied to transformer primary is increased by keeping V by F ratio is fixed. Here they have given V by F ratio fixed, I mean constant. If you want to make V by F as fixed, if you increase the voltage, then automatically frequency also increases. Then only you will get the fixed. Then magnetizing current and the core loss will be representatively dash. So V by F is fixed means WH is proportional to frequency, W is proportional to frequency square. Okay, frequency square. So if you increase the voltage, automatically you have to increase the frequency to get the constant. So as frequency increases, losses will be increases. Okay, so losses will be increases, and the frequency increases. Then what about the magnetizing current? Magnetizing current is depend upon B max. Here B max is constant na? Why? Because V by F is constant means B max is constant. So magnetizing current is constant and core losses will be increased. So the answer is option D. Okay. So magnetizing current is depend upon the B max. B max is constant. Why? Because V by F is constant. Coming to the next question. In given in given transformer for a given applied voltage, losses which remain constant irrespective of load changes. Which losses are constant? Core losses. I mean iron. So copper losses not friction index. Hysteresis and eddy current losses. That is iron or core losses. The all-day efficiency of distribution transformer will be high at low dash. Distribution transformer generally operated 50 to 75% of the. So that means here iron losses dominated. As less load means iron losses are dominated. So we have to reduce this. I have already given this in the previous session. To get minimum iron losses. Okay, with low iron losses only, we can get the efficiency will be maximum. In case of power transformer, efficiency is maximum whenever minimum copper loss. How to minimize the copper loss. For 100% efficient, very good question. 100% efficient of the transformer, the primary turns has 1000, secondary turns has 100. If the power input is 100,000 watts, then what is the power output? We know power is constant, magnitude of power is constant. Okay, only you are getting the losses means the output power may be a little bit less than the input power. Okay, just voltage and currents are changes with respect to the turns. 100% efficient means power output is equal to power input na power input. So power input is 1000 means power output also 1000. So the answer is option B. Okay, power input is 1000 means power output also 1000. And coming to the next one, hysteresis loss occurring in the material does not depend upon which of the following parameters. Hysteresis losses depend upon zeta, B max, power 1.6, F into V. So depends upon flux density, hysteresis constant, and also frequency, but it does not depend upon reactivity. So the answer is option D. Okay. So the answer is the advantage of putting tappings at the phase ends of the transformer. Why we require tappings? So to get the variation, of the voltage. Generally, it is provided in a HV side. Okay, for example, it is 1100 volt. You can make the tapping for 440 volt or 230 volt like that. According to your requirement, you can vary the voltage. Okay. And the next one, percentage R, percentage X, and single phase transformer having constant losses. So iron losses they have given 1%. At which we will get the maximum efficiency. At which load means X na root of iron losses by full load copper losses. So iron losses are constant losses, they have given 1. Full load copper losses. If they have given percentage R, these are nothing but you can say copper losses. Due to resistance, I square R only we are getting losses. Na? That is 2%. 1 by 2 means 1 by root 2, 0.707 of the load. So the answer is option. Okay, 0.707 of the load. So the answer is option. Coming to the next one. A transformer has maximum efficiency of 90% at full load unity power factor. The efficiency of the transformer of the half of the full load and same power factor. For half of the load means the efficiency may be a little bit less than 90%. So the options are A and C most probable, but we have to, these are very near to each other now, so we have to calculate only. Okay. So here maximum efficiency. Okay, so maximum efficiency is 90% given. So when we will get the maximum efficiency? Whenever the copper loss is equal to iron losses. So from this 90% means 0.9 is equal to x into kVA. Full load given na x is 1. So kVA, let us take 1. Power factor is 1. They have given 1 into 1 into 1 plus losses. Losses means iron losses plus full load copper losses. Okay, full load copper losses. But according to the maximum efficiency, where both are equal, Pi plus 2 3. Iron losses Pi, copper losses P copper loss. So at maximum efficiency, both losses are same. That means copper loss will be equal to iron losses. Then in the place of copper loss, if you place iron losses, you will get 2 Pi. So 2 Pi. Okay. So from this one, we can calculate the iron losses. You can calculate the iron losses. So you will get iron losses approximately 0.055. Okay, then you are going to find out efficiency at half of the load. Whenever the half of the load x is half, half into 1 into 1, half into 1 into 1 plus 1 is nothing but kVA. This is nothing but power factor, guys. Don't confuse. Here iron losses. Iron losses are at any load. These are constant. Copper losses at half of the load. Half square into iron loss na 0.055. Okay. So if you calculate, you will get approximately 87.8%. So answer is option. Later can calculate this one by using your calcs. Okay. Coming to the next one. P1 and P2 be iron and copper losses of a transformer at full load, and maximum efficiency of the transformer is at 75% of the full load. And then what is the ratio of x? X of the full load given, x is equal to 75%. That means 75 by 100, that is 3 by 4. Okay, they are asking ratio of P1 and P2. We know x is equal to root of iron plus full load copper loss. Iron losses they have given P1, copper losses they have given P2. And x they have given 75%, that is 3 by 4. So square it just, if you square it 9 by 16 now, so that is the answer only. That is the answer only. The ratio is 9 by 16. Okay. Coming to the next question, guys. A 4 kVA transformer has iron losses of 200 watt, full load copper losses of 200 watt. The maximum efficiency at a unity power factor. Maximum efficiency at unity power factor. Okay, so x into kVA, x they have not given, so 1 kVA. What is the kVA given? 4 kVA, that is 4000. Let us take 4000 VA. Okay, why I have taken 4000 here? They have given in the watts, so I am going to take here VA into power factor. So power factor is unity given. So here also 1 into 4000 into 1 means 4000. So 1 into 4000 into 1 plus iron losses. Iron losses are constant, 200, and full load copper losses. Full load copper losses also they have given 200 watts at full load only, so that is 200 only. Okay, so here we have to take the copper losses are is equal to iron losses. Okay, so here these are the iron losses, and copper loss are also, for example, if they have given this one as 400, 600, 800, whatever it may be, we have to take to get the maximum efficiency. Copper losses are also equal to iron losses only, that is 200. But here they have given same value, means no need of confusion. Okay, so if you calculate 4000 by 4400, so that means very near to the value of 1, so that means here you will get 90.9%. so the answer is option A. Okay, answer is option. Coming to the next question, in a transformer if the iron loss and copper loss are 40 and 50 respectively, what is the, at what fraction of the load you will get the maximum efficiency? So the same, x is equal to root of iron by full load copper loss. Iron losses are 40, full load copper losses 50. So 80 by 100, that is 0.89 you will get. So the answer is option B. In the following, which machine has highest efficiency? We know very well transformer having very high efficiency among other. Remaining all are rotating type of machine, is a static machine, so losses will be less, so high efficiency. Okay. Efficiency of a power transformer is in the order of dash. Generally, the efficiency of the power transformer is more than 95%, that is 98% given. So we have to select the answer as 98%. Okay. And the next one, regulation based question. We will discuss the regulation based questions in the next session. Okay. Students, if you like my class, please click on like button and also share these videos to your friends. Okay. And express your intention with your comments. Okay, if you have not subscribed, subscribe the channel. Okay, and I have also given Telegram link in the description box. Click on that one and join in that. Okay, students, we will meet in the next session. Thank you so much.